Okay, good. So this is the first time I will not be needing pointer. I can just use my crutches and we are good to go. Okay, so first some quick brief introduction and disclaimers. So my name is Martin. I'm from Google DeepMind in Edmonton, Canada, and I previously worked for IBM Watson. As a disclaimer, everything I will be telling you today is just my personal opinions, and none of it has anything to do with Google, Google DeepMind, IBM Watson, or Charles University. So anything I say, don't take it as a granted. That's the DeepMind's point of view. Okay, disclaimer is done. Let's do it. So what I plan to do today is we will first have a quick look at a historical overview of games as a benchmark of artificial intelligence. Then we will look into game theory and optimal strategy. So what I would like to do first is to look at all the algorithms that people like to do, whether it's chess or whether it's a Go and all the other games. They just use these algorithms, they work, but they don't necessarily look at it the way we game theorists like to look at it. What's the strategy they actually want to find? And once we look at it maybe in the right way, we will see why these algorithms fail to work in other domains as well. And finally, DeepStack will come to rescue, and we'll get these algorithms running for other domains as well. Okay, so quick overview of historical benchmarks for an AI. So maybe the first nice one was in '92 when Jerry Tesaros TD Gammon gained a human level gameplay in backgammon. So what was important about this milestone was that this was done just solely from a self-play. The AI was improving because it was playing itself, and it was also using neural networks for an evaluation function within. So this was a real eye-opener, that something like that, just a pure self-play, and neural networks can learn to play competitive level of a game that the humans like to play. In 96, 97 came the result that probably everyone still thinks of as the big man-machine match that happened, and that was when IBM Deep Blue managed to beat Kasparov. At that time, he was the world's chess champion. The IBM Deep Blue managed to beat him at chess. So this was also a huge event. So the important thing was not only that a huge machine was necessary, it was also about how do we do the search, how do we evaluate the functions. And in a sense, this will be closely related how the DeepMind's AlphaGo tackled game of Go. Okay, let's move on a few more years. And in 2008, Polaris. This is something that not many know of. This was the first time that humans were defeated in some small poker variant. It was small enough for computers to be good at, but it was large enough so that humans at the time tend to play that online. So it was at limit hold'em poker, and that game it's not played anymore online. But during the time it was quite popular, and it was for the first time humans were beaten in an imperfect information game. And as we will see today, imperfect information games are way different beasts to be tackled. So this will see at another milestone. Okay, moving a few more years ahead, and in 2011, yet another important game milestone, and it was IBM Watson Jeopardy. Interesting thing about that was the input was not well structured. If we have Go, if we have chess, if we have poker, the input has a very neat and simple structure that computer can understand. But in the case of Jeopardy, the input was just natural text. So the challenge was, can we understand the natural text well enough so that we can beat the humans in this game? So that's why it's in here. So in 2013 or 15, depends on the way you look at it, it was an archive around that time, but it got a nature cover in 15. That was when yet again DeepMind managed to create not on all of the games, but at most of the old Atari games, human level results, just from playing from pure images. So the important is yet again, there's no inherent structure. We just see pixels as an image, and we just train a neural network and Q-learning or whatever we use now later on to play these games. So this was a big deal. Later on, yet again, DeepMind and neural networks. The AlphaGo managed to beat pros in Go. This is a game that's not that popular as chess in the Western world, but it's way more popular in Asia. And the important milestone in here is how the evaluation function worked, and also how the evaluation function was plugged into a search. While in here, the search was more or less vanilla local look-ahead search, where they used, in a sense, a human-designed evaluation function. That is, if you have more pawns, you are better off in the chess situation. In here, the evaluation function was learned from a self-play, like a reinforcement learning self-play, and the evaluation function was used not just during like a few-step look-ahead search, but during a nicely designed Monte Carlo search. And finally, this is the result we will talk about a bit today. In 2017, DeepStack, this was nature cover, this was a science cover. DeepStack became the first algorithm to beat pros in no-limit hold'em poker. And also the important thing was not that we managed to do it, it's also how we did it. The important piece is that all of these great ideas in here, that is using neural networks and as value functions, doing a look ahead local search and all these things, they seem to be impossible to do in imperfect information world. That is, in a world where you don't have all the information about the state of the world. In chess, in Go, in backgammon, all you need to know about the world is just right there. You see a board, and there's no hidden information. While in poker, and in a sense in the real world as well, there's always some uncertainty about the state of the world, right? And that's why poker is an interesting game for scientists, and that's why this result was so important. That we finally have algorithms that work in some way very similar to the way AlphaGo works, but in imperfect information world. Okay, so this is just a table that I want to skip for now, and let's look at like a big two things how people tend to approach games. So, if your task is to design a computer program that's supposed to play chess, two things that people typically do is it can be a self-play or a Minimax or an algorithm that you use to find an optimal strategy in a small game. So first we will have a look together what it actually means. What does it mean to play optimally a game? Because that's something that people just like tend to ignore a bit. And then when the game is too large to be solved perfectly, people tend to use some sort of like a local search methods where they don't solve like a full chess game in advance, but they are the reason as the game progresses. So these are two key components that I want to look in today. Okay, so in particular, we will look into self-play in a sense like what does it do, what it means for a self-play to stabilize to a solution that we care about. When does it converge? Does it converge at all? And what strategy do we actually care to find from the self-play? And as we will see in Minimax as well. And then we will look into the second part of it, that's local search. And that's the idea of solving the situation or reasoning about the situation only when it happens, not in advance. That seems to work, right? That's like reasonable. We will just, as we see the board, we will think about the board as it happens. But that inherently has this hidden property, and that is you just expect to be able to to solve independently all these local subproblems as they happen, and hope that in global solution, that is, if you combine all these locally optimal solutions together, they form a globally optimal one. So that seems obvious, and it works for chess and Go, but it does not work for imperfect information games. Okay, let's do the first bit of the presentation, and that is self-play. Okay, so what is self-play? It's this very simple idea that you start with a strategy for 2 players. So let's say I want to find a strategy for chess. So I will have a black and white player, and I will start with a naive strategy. This is black and this is white, for example. And this is an iterative algorithm that at every single time I will improve a strategy of one player so that it's better against the current strategy of the opponent. And then I do the same thing for the opponent. And I go on and on and on and on. And the idea is, the idea seems to be like obvious, right? Like when I get a new strategy that's better than the previous one, if I do it long enough, I will get an optimal strategy. That's a self-play. That's a self-play how to do like Jerry Begemon did self-play. That's a self-play like AlphaGo uses self-play, and that's a self-play that people tend to do. But what does it do? So to look into more details, what does self-play do in particular, we will need a bit of formalism. It will be very light, I promise. So all we will need is to represent a strategy of a player. So typically in game theory, it's denoted as sigma. Strategy for other players, it's typically denoted as this guy, and a strategy profile is just a strategy of all players. So if it's just a 2-player game, this will be just sigma 1 and sigma 2. And utility, that's just how much do we win given the strategy profile. So this guy, this function, takes as an input strategies for all the players and tells me how much does this guy wins. So that's all the formalism I will need in here. Let's keep it very light. Okay, so once we have all these letters, we can just write down what self-play does, and it's a sequence of strategies. So these are the strategies for player 1. So this is at time 1, 2, up to a time t, and these are strategies for the other player. So it's not just an arbitrary sequence of strategies, but it's a sequence of strategies so that this thing down here holds. And the only thing that this thing tells us, that once we are selecting the next strategy for this guy, it will do better versus the opponent strategy at the time than the previous strategy. So all we really do, we just look at, if you go in here, we are doing this improve step. We look at the strategy of this guy, we look at the strategy that we had previously, and we improve our strategy based on the opponent strategy. And we can keep doing that on and on again. Okay, so what if we are lucky and this guy just converges? We find a stable solution that is like we are doing this self-improvement thing, and at some point the strategy does not change at all. So what does that mean, that we were lucky and it just doesn't change anymore? Like, so what can we tell about that strategy that we converge to and seem to be optimal because we cannot improve anymore, right? Like the self-improvement just got stuck. So if you just rephrase what I just said, that is, you cannot improve the strategy of the player, and you cannot also improve the strategy of the other player. It's just saying that none of the players can improve, and it turns out that this is the very definition of Nash Equilibria. So what we immediately get is that if we just run self-play on any game, we are lucky that the self-play just like stabilizes. The strategy that we have right now is Nash Equilibria. So that's great. We've been lucky, and we will use just Nash Equilibria in these settings. But is it this the strategy we want to use? What can we tell? What are the properties of the Nash Equilibria? So suppose we we were lucky. We just found a solution, and now we are going to play our piece of the strategy. That is strategy, let's say, for the white player, and we are going to play a guy that we have never seen before. So what is he going to do? Let's say he's a suboptimal opponent, and even though he knows what we are going to play, he's not going to optimize his winning. Like, he's not going to best respond to our strategy profile. He's not going to maximize his utility. He's going to just do some stupid things. So we were trying to find a super good strategy for a game, and then we are playing just a random guy from the street who doesn't really know how to play this game. What's going to happen? So just the property of Nash Equilibria that none of the players can improve doesn't really tell us anything about that particular scenario. It could very well be that the guy that's going to play us is going to do something really stupid, and he's going to get suboptimal reward. That is, he will do something that will hurt him, and he will win very little money, but that doesn't necessarily mean we will win a lot of money. You can easily construct games where opponent's mistakes not only hurt the opponent, but these mistakes will also hurt you badly. So that doesn't really sound like a great property to have. Like, why would we want to play this Nash Equilibria strategy at all? So this is the moral of the story. If you play this strategy, it doesn't sound such a great idea. So, but we don't play any game in general. We play chess, we play Go, we play poker. And what these games have in common is that they are strictly competitive. That is, whenever I win, opponent loses, and the same thing can be told about the amounts of winnings, right? Like, whatever money I win, opponent loses, and vice versa. So these games, these strictly competitive games, in a sense, with two players, we call them two-player zero-sum games. And using the formalism we already had, we can just put it in here as this. It's super easy to formalize this property. Okay, so this property is going to help us. And how is it going to help us? If we go through the very same reasoning I just told previously, we are going to play our part of Nash Equilibria, and we are going to face some suboptimal guy. Now we can use the zero-sum property to show that any suboptimal move the opponent makes, we can only benefit. So, and it's like a free line proof where we just plug in the zero-sum property of the game. So this is great, right? Just having a zero-sum game fixed our solution concept. Suddenly the strategy that the self-play found doesn't seem so bad at all. So this is great. Like, we do want to play Nash Equilibria. At least I hope that I convince some of the people. So we have an algorithm that if stabilizes, it stabilizes in this particular strategy, and we also know it has nice properties. But does it have to? Does it have to stabilize? When does it stabilize? Are there some games where it doesn't stabilize at all? So how about rock, paper, scissors? This is a super simple game, right? You have just 3 actions. Opponent has 3 actions, and let's run alpha 0 or whatever on rock, paper, scissors. We will get like a sequence of self-improving strategies. We will first play rock, then we play paper, then scissors. At every single time, it's still self-play, right? Like the property that the next action is better off than the previous one, that holds true. But if you look at the sequence, it just doesn't converge at all. At every single time, we will play just one action. And why is that? The self-play as we typically implement it, if you look how you would implement self-play in AlphaGo or something, you've got this like arc max or max sort of thing, where you just maximize over all the actions possible given an evaluation function, and then the action you play is the one that just maximizes the winnings. So at every single time, these kind of algorithms will just produce a deterministic strategy. Whenever you have these like argmax things that just maximizes, you are going to have deterministic strategy. So this is set, right? Like the thing that works for chess, works for Go, suddenly doesn't work for rock, paper, scissors, even though it's a super simple game. So, but like I don't do self-player. I just like run a Minimax, like small game search tree, or I do like some pruning, like alpha beta pruning or whatever. So what if like that says me no it won't. Like it's like for these games that I just mentioned, it's still the same. Like it will give you Nash Equilibria, and when are of these games that where it works nicely, it just breaks. So maybe it's not the fault of the algorithm. Maybe it's not self-play. Maybe it's not Minimax. Maybe it's not Monte Carlo. Like maybe these algorithms are still sound. It's just that the game is broken. Like maybe we have good algorithms, but the game doesn't have the strategy I care about. Maybe it doesn't have Nash Equilibria. That's why I cannot find it, right? It's not the case. We have a term from the 50s that says basically that every finite game is guaranteed to have this strategy. So we know that the strategy has nice properties. We know that the strategy exists, but the algorithms that we like to use in chess or Go fail to find that strategy even in rock, paper, scissors. So what's the crucial point in here? It does exist, but sometimes in some games, the strategy needs to be stochastic. In rock, paper, scissors, it's not hard to see that the optimal strategy is to play uniform strategy across all the possible actions, and that none of the pure strategies are optimal. So that's the key point. All of the algorithms that people like to use, Minimax, pruning, self-play, they quite often just produce deterministic strategies, or even if there are slight modifications on these algorithms that may produce stochastic strategies, they don't have the right properties that we care about. They do not converge to Nash Equilibria in these games. It turns out that poker is like rock, paper, scissors. It's theoretically much closer to rock, paper, scissors than it's to Go or chess. Why is that? That's because we need stochastic strategies to play optimally. So let's have a look at the game of rock, paper, scissors. So there are many ways how you can model this game. One of the ways is via this simple table. People like to call these normal form games, but you can think of it as a simple table. And the guy. There's a column player, and there's a row player, and there's just a reward in here. You can see that it's zero-sum game because the reward of the column and row player always sum to 0. Okay. So as I said previously, this game is guaranteed to have a Nash Equilibria. I will also tell you that the Nash Equilibria is a uniform strategy. But we need a different family of algorithms to find an optimal strategy in these kind of games. So there are algorithms that are guaranteed to find this optimal strategy in these kind of games, and there's actually plenty of them. So one way is to create a linear program that for which the solution of the linear program is guaranteed to be Nash Equilibria. Typically, this linear program is roughly of the size of the matrix, or if the game is better to be represented in a tree, right? Like you would probably not want poker because it's a sequential game to be represented in a table, even though you can. But trust me, you don't want to. You can represent it as a tree. And there are ways how to construct a linear programming that's in a sense nice for this tree-like representation. So that's one way you can solve it via linear programming. The other way you can do it, there are self-play-like algorithms that produce strategies at every single time, and these are guaranteed to converge. Like there are specific algorithms for these kind of games. Some of the algorithms convert faster, some of them convert slower. They might have different properties, but there are algorithms. So we will now have a quick look in one of the algorithms. This particular one is super popular in computer poker community. And I will explain in a bit why. So regret matching, it's yet again an iterative algorithm that works in a sense as a self-play, but we are going at the next step when we are going to select like our strategy at time t+1. We are going to use a slightly different formula to select next strategy. We are not just going to select like a best response or whatever. What we are going to do, there's a very simple way to implement it. At every single time, we will look at the reward we have made so far. That is, we played this strategy and the opponent played this strategy. Then we play this strategy and the opponent played this strategy. And every single time we will look at the reward we have made and then just sum it together. And then we will do like a what if or counterfactual think in our head and say to ourselves, well, what if rather all these times we just played action A and compute the reward of what if that happened. And we will do it for every single action available in this game and compare this value to the value we received so far. And this value is called regret. So this is how much do we regret not playing this action all the time. And it turns out that the regret matching is very simple formula that at the next step you just select a strategy that is proportional to the positive regrets of this action. That is, if there's an action that I regret negatively, not playing, that is, I do not regret not playing this action, I'm not going to play it next time. But if I have two actions I regret not playing, I will just play them proportionally according to these regrets. So at every single time, I'm likely or I can produce a mixed strategies because it's just proportional to the positive regrets. Important thing to note is it's not the strategy at the end of the sequence that's guaranteed to converge to Nash Equilibria. It's the average strategy that's guaranteed to converge. So that might be surprising, but you need to keep averaging the strategies properly so that you are guaranteed to converge to Nash Equilibria. So this is not the only way to get there. I'm showing this guy because it's the most popular algorithm in computer poker community. It has a reasonably nice guarantees. Like it's on paper, it's not the fastest algorithm possible. Like the bounds are not the best we can do on paper, but in practice, it turns to be faster than the algorithms with better bounds. And it's also super easy to implement. Just doesn't work. Okay. Okay. So this is regret matching. Super easy to implement. It will convert. You can implement it in MATLAB in like 10 lines of code if you have a matrix game, and you will see it convert. There's also the reason I also put it in here, there's a reasonably simple and efficient way how to run this sort of an algorithm, not just for matrix games, but to also run it in a tree-like games. That is, if we have a tree representation of a game, such as poker, we can run these regret minimization algorithms in a sense independently in all the nodes of the tree, and we can show that the total regret or the total epsilon, in a sense how close we are to an optimal strategy in the full game, is in a sense bounded on all these like partial regrets in all the nodes available in the tree. So it's very nice and easy to implement that as well. Okay, so this is great. We have an algorithm that works for these games. We can also run it in a tree. So why don't we just do it for poker? Well, why don't we just run Minimax or self-play in chess? Because the tree is just too large, right? It turns out that the tree of poker is even larger. The number of nodes or the number of information sets is larger than the number of atoms in the universe. So there's no way I'm going to run the algorithm I just showed you in every single node of the game tree. Okay, so what do we do? So when people do these kind of algorithms, they don't also run like a Minimax on self-play in the full representation of the chess. What they rather do, they run it only locally. So this is how it looks. When we have a game of chess, Go, or even like a decision planning or stuff like that, we don't necessarily take a full game of chess, represent it in a table, and run Minimax on it. What we rather do, whenever we are to make an action, we just reason about the situation that we can see right now. And the way it typically looks, we will look few steps ahead. If we are lucky enough and we are close to the end of the game, these few steps will get us to the end of the game and we can reason perfectly. If we don't have the time to reason all the way to the end of the game, because like there's still plenty of moves to be made, what people often do is they just cut the look-ahead tree at some depth. Let's say like I will just search 10 steps forward, and all the nodes or the situation steps 10 steps ahead, I will just guess how good that situation is. And this guess can either be like a heuristic function that domain expert will write down. For chess, it can be, oh, I have a queen more, so I'm probably going to win. Or in AlphaGo, it can be a neural network that's trained via self-play and will evaluate the situation. Oh, I'm better in this particular situation. So this idea is very general. It's used everywhere, and it doesn't necessarily have to be like this cutting few steps after. We can like even Monte Carlo tree search, all the things that AlphaGo do fall within this framework of like reasoning about the situation when I am in that particular situation. All these algorithms fall within this framework. Okay, so that's good. That sounds like a reasonable thing to do, right? And it is a reasonable thing to do in chess, in Go, but it's not a reasonable thing to do in poker. Why is that? So, as we have been reasoning about this situation locally, what we expected is that when we solve the local situation in a sense optimally, we hope that as we solve all the local situations independently that we will experience during the gameplay, that the total strategy, that's a union of all these local solutions we have made so far, will produce a good global strategy, the Nash Equilibria that we care about. But yet again, rock, paper, scissors. Oh, sorry, it's not that nice, but whatever. So, another way to represent rock, paper, scissors is not just via a table, but you can represent it via this tree. This kind of tree game theorists like to call extensive form games, and the trick is, in imperfect information games, there are some, when you are about to act, there are some situations that you cannot tell apart. Like in poker, you cannot tell apart what cards the opponent is holding. In rock, paper, scissors, one way to formalize this game is to make the opponent act first. But the opponent is not going to tell me what action he has made. So when I am to act, I cannot tell apart whether he played rock, paper, or scissors. So when he played rock, paper, or scissors, all these nodes I'm going to merge into an information set. And I have to play the same strategy in all the nodes in an information set. In other words, the strategy or the behavioral strategy is a mapping from the information sets to the actions available in there. I cannot play differently in here and play differently in here. So that's one way how to look at this game, and not surprisingly, it's also a nice way to look into a poker, since it's a sequential game. So I'm going to have a tree-like structure in there, like the people will like alternate playing there, the dealer is going to deal some cards. So these extensive form games are a nice way to represent these games. So let's say I'm going to do a local search from this information set on, and I know that Alice, or in my strategy solution I have so far, the guy playing previously is playing optimally. That is, he's going to have a uniform distribution over all his actions available. So that I do know, but that has happened, right? Like I'm only going to act now. I am going to reason locally, and that's here. This is my action. So what's an optimal action for Bob in here? If he knows that Alice made an action, and the distribution over the rock, paper, scissors actions she has available is uniform. So what's the locally optimal solution for Bob here? I'm going to grab a water in the meantime. Okay, so it's not hard to see that locally optimal decision for Bob is any strategy available. Playing rock, given that there's a uniform distribution in here, gives him the same value as playing paper or as playing like uniform strategy, which is optimal. So suddenly I'm going to play a locally optimal strategy, but playing always rock is clearly not Nash Equilibria. So this local reasoning breaks in rock, paper, scissors, and it breaks in poker as well. Okay, so we do have an algorithm that works for small games, but we are screwed to reason locally in large games. So, see in this picture what people decided to do, rather than trying to fix these local reasoning algorithms for poker-like games, they decided to do other thing. What they decided to do is they said, okay, I have an algorithm that can find a strategy solution in small games, and I have a large game. I'm just going to squeeze the large game into a small one. This was called abstraction, and this was up until recently the state-of-the-art technique of solving large imperfect information games. You were to create a smaller abstract game, and you hoped it's strategically similar to the one that you care about. Then you used, for example, the regret matching we have seen to solve the smaller game. And then you somehow try to map the strategy from the smaller one into the larger one. This is yet another picture. And I said up until recently, and this picture in particular is from a science paper from 2015. So in a science paper of 2015, there was explicitly this note, like leading approach to imperfect information games, and the theory was, we have a too large of a tree, we will make it smaller, we will solve for Nash Equilibria, and then we will map it back. But what does it mean? How does it work? Imagine doing the same thing for chess. Rather than doing local search technique, we would squeeze the chess into a small game, run our favorite algorithm, it can be Minimax or a self-play, found an optimal solution in here, and then try to play the strategy in the large game. Like it's not hard to see that it might fail badly in chess. And it did fail badly in poker as well. How badly? So these are all the state-of-the-art poker AIs in 2014, 2016. And this guy in here is a strategy that everything it will always do, it will fold a card. So I'm not sure how familiar with poker you are, but folding means that you will just like leave the cards, lose the bets you have made so far. So the strategy, even when dealt like a pair of aces, it will always fold. Every action it will do is always fold. And that strategy, when we look how close to an optimal strategy that is, how close to an Nash Equilibria from an exploitability standpoint that is, we know precisely how close that is, and that's this line. It's simple enough strategy to compute the best response, or like how close we are precisely. For all these guys, we don't know how close that is, but we have a techniques to get a lower bound on the epsilon. And even the lower bound on the epsilon, like how close to an optimal strategy we are, that's like 4 times larger than always fold. So maybe this picture is not an exaggeration for poker as well, right? If all the techniques just produce this. So looking more into like how bad it was up until DeepStack. In 2015, there was a first shot to beat players in this large, like no limit hold'em poker, and people played 80,000 hands of poker. And even though humans were beating the computer quite badly, because of the huge variance inherent in poker, it's not like chess where people tend to play reasonably few games. In poker, you need to play a large number of samples to get like a reasonably statistically good results. Even with 80,000 of hands and humans crashing a computer, the result was not statistically significant. It was real close to like a statistical significance we would care about, but it was not quite there. In 2016, not only there was this graph I showed you, there was also a 10-line poker AI that was able to beat the top agents at the ACPC competition, which is like an annual competition of poker AIs. So even 10-line script could beat all these strong participants. And 2016, that was the previous graph I just showed you. So that's 2016, and everything looks set. Okay, so abstraction clearly doesn't work. It wouldn't work for chess as well, so it doesn't work for poker. But computers still can beat humans in like chess or Go, even though these are large games. And why? Because they just don't squeeze the game. They reason locally. So let's reason locally in poker as well. And how do we do it? DeepStack can do it. So it brings all the goodies of local search, like these evaluation functions, the local reasoning, all these kind of things that are great. We want to use them, but we were unable to do up until DeepStack. The algorithm itself, we call it continual resolving, and as you can see, it's very similar to just a local search. We reason from the current situation, except that previously you just reason from the current situation, given the current situation, and nothing at all. We start the reasoning process using 2 special invariants that we keep updating as we play on. You can think of these invariants as some information necessary to reason about all the possible states you can be in right now. Like your opponent can be holding like large number of different hands that you can see, and also in the very same situation, you are just holding one hand, but you could very well be holding all the other hands as well. And these invariants help you to reason about all these situations at once properly. You will again evaluate some leaf nodes during a look-ahead search using a value function, but this time the value function is not going to produce just one number, but it's going to be a vector value function, and yet again you can think of it as values for all the possible situations I can be right now. And we will do the very same thing we do in here. We will find a strategy using this method, make an action, update these invariants based on the action we have made, and repeat. So this is okay. So this is roughly how it looks, even though it's yeah, I'm sorry, it's not very informative, but it was in the science publication, so I stole it. Okay, so this is just saying what I told in here, but maybe let me explain what these invariants that we have to keep track of and update properly are. So we have two invariants in red and green. So we keep track of agents range. What that is, it's a belief or a probability distribution over all the possible states we can be in. So that we can compute given our strategy easily. That is, it's a probability distribution over all the hands or all the cards we can be holding given this situation. It turns out all you need to compute for that is to know your strategy. You don't need to know strategy of the opponent. So we don't care who we play against. And we also need to keep a second vector, and that vector is maybe a bit more interesting. That vector fixes the thing we've seen in Rockpaper Scissors, where we were unable to solve it locally so that we don't break globally. This vector, that's one value for every single hand of the opponent, or more general, every single situation the opponent can be in, and that value gives us a bound on the value. And what we do, our reasoning process finds a strategy for us, for player number 1, so that player 2, with none of the hands he can be holding, gets a larger value than this bound in this vector. So this is a crucial property to have. I'm not going to go into details, but roughly these are two things that we need to keep track of, so that the local reasoning can be implemented properly, so that we have all the nice guarantees that if we have these value functions that are like good enough and we run the local search long enough, we are close enough to a Nash Equilibria. Like this algorithm is sound. It's not just like we did some heuristic so that it works for poker. We have some nice guarantees. So this is a machine learning meetup. So finally some neural network. So the neural network, we use it for evaluation of the situations. But as I said previously, a poker situation is not just about what we see on board. It's not just the cards dealt, or it's not just the board of chess or Go. It turns out that in order to reason properly for the local situation, you also need to keep track, or you need to also reason about all the possible states and the beliefs over these. So the neural network that we invoke at every single iteration of the regret matching as an input not only gets the situation on the table, but also gets as an input two vectors, two probability distributions for all the possible states that we can be in and the opponent can be in. Also keep in mind that these vectors, they update every single iteration, since the regret matching is a self-play-like algorithm, so that it produces strategies for the players, like every single time it produces a new strategy for the players. And this probability distribution that we feed into the neural network can be computed via a simple bias rule from this strategy of the players. So every single time the board is the same, but the probability distributions they differ. So what the neural network gets is probability distribution of one player, probability distribution of the other player over all the cards they can be holding, and it also gets some representation of the situation on the board. Like in poker, it's all the bets that has been like made so far. It's the cards that were dealt on the board. Then we have like few feed forward, like fully connected rules and all the good things that people like magically plug in together to get good values. The thing that's slightly different from like a vanilla fully connected network is that we know that we are in a game of zero sum. So our neural network is wired so that it's guaranteed to produce values that correspond to a zero-sum game. So that adds a little bit of bias that maybe helps us to learn faster. And the output of the neural network is one value for every single situation the opponent can be in. So in a sense, it's given the beliefs I have about the cards of the players, I know what's the value of holding, let's say, aces, given this belief. So not surprisingly, holding aces is very different if opponent thinks I'm holding aces or if opponent thinks I'm holding a weak card. So that's like an intuitive way to see why it works for poker. But yet again, DeepStack is a general algorithm that's guaranteed to work for any imperfect information game. Okay, and it works well. So 10 more minutes, sounds good? Awesome. Okay, so it works well, people like it, and so this is a bit older slides, but we, as of, I think it was May or March, I don't know. So as of May of March, we also got a cover of Science. If you see the cover, it's this like nice and sexy ace of spades. So I really like it. I like it because I designed it. And so what's important? And not only that this algorithm is very neat on the paper, like we finally have a local search like algorithm for like these games where we cannot see all the information. It also works well in practice. So we ran the algorithm versus like a set of 40 poker pros. If you look, maybe just consider just the players that finish the required number of hands. We ask all the players to play 3,000 hands of poker. And in here, this is how much DeepStack was winning versus the player. And in here, I think it's 95% confidence interval. So you can see DeepStack was playing so well that only from 3,000 hands, for every single individual, every guy that finished the 3,000 hands, except of the first guy, we can say that we are statistically significantly beating the guy, and we are also beating this guy. It's just not yet statistically significant, only from 3,000 hands. And if you recall, the last man-machine competition, we did 80,000 hands to get no results at all. So the last few things I'm going to comment on. So this in here, you can see it's called like adjusted win rate, and in here it's unadjusted win rate. And the interval in here is much wider, right? Why is that? That's because we as some of the goodies in the paper as well, we also introduced a new technique that reduces variance in imperfect information games. And the technique is provably unbiased. That is, if you use the technique on your data, it's guaranteed to give you on expectation the same number that you are about to see from the data, but it's going to reduce variance rather drastically. How well? Roughly 10 to 40,000 times less data are needed using this technique. So these 3,000 hands are about the same statistical value as if every guy was playing like 500,000 hands versus DeepStack. Oh, sorry, no. 40,000, okay. Multiplication is hard. Okay, so the variance reduction. So variance or noise is like an inherent problem in many domains, and it's easy to see that it's an inherent problem in poker. If we didn't use it, we would use like 100 or hundreds of thousands of hands to get any meaningful results. And the variance reduction that you can do, maybe the easiest way, like that's not hard to imagine, that it's unbiased, like you are not going to bias the results. If you use something called mirrored hands, and that is, you will, let's say you are going to play computer A versus computer B. So you are going to run it on 2 instances, and one instance is always going to get the same hands, but just mirrored on the other machine. And if the computers cannot communicate, like, oh, hey, I got these hands, you are probably going to go get these ones. You are not going to bias the results, but this simple technique is probably going to help you to reduce variance. But it's compared to the variance technique that we introduce, it's very weak. Long story short, I'm not going to go into details. It's all about control varieties, but it's we are applying the control varieties in a nice way that fits imperfect information games properly. And the best thing about that is, in order to apply control varieties, you need, in a sense, some estimate of the value of an action we are going to make. and if that's correlated with the value that you are going to see, the variance is going to go down. And the estimate itself, it turns out that we can just use the neural networks from DeepStack anyway, and these are well likely to correspond closely to the value of the action we are going to make, because we just traced the value. So this turns out to be well correlated, even if we play like a human, not just a machine. Okay, and even though I have some more slides, I think they are not important for the rest of the talk. So, okay, we are done.
Okay, and if there are any questions, I will just pass you the microphone. So, do you have an example of another domain you were able to solve with the DeepStack algorithm?
So I know the guys from Czech Technical are doing like exactly that, like I think Karolis. Like I don't know how well ahead you are, but I roughly believe like you are like your PhD is about applying DeepStack to other domains. So
yeah, we are trying to apply to more complicated games like tic-tac-toe or chess, where you have imperfect information and there are some more things that needs to be taken care of. So, for example, private information is not constant. So I can tell you a bit more in detail later.
Yeah, like unfortunately, like it turns out poker has this very neat structure, so that DeepStack works very well in there. For other games, it can get quite messy.
Okay.
What about the parameter which is about the money? I mean, there's a budget and the computer was bluffing. The players were not able to bluff, or I didn't see the parameter here. But when you play poker, you play money, and you can win with no hands.
I see. Okay, so it turns out bluffing is not a human concept. It is just an inherent. It comes out naturally from the rules of poker and playing it optimally. So that's a neat property. Like you can think of it. So some chess openings, like the chess openings, are in a sense a human concept, right? Like this like Sicilian opening and so things like that. They are a human concept, but maybe if you are to play optimally, you just need to use these openings. And in poker, on small poker games, it's easy to show that if you want to play poker optimally, like the algorithm itself learns to bluff. It needs to bluff if it wants to play according to Nash Equilibria, it needs to bluff.
I just have a quick request for the last slide that you showed. There was something interesting. If you could just fast forward to the very last slides, there was some interesting information.
Maybe that's why I put it back, because it was too interesting. So, like, you want to go forward? Yeah. Oh, okay, that's why I put it back. No, no. So obviously, like, what would be like people often ask, like, what is the next thing? So clearly, an interesting challenge is to do it multiplier, but unfortunately, it's not as easy. There are like all the things we talked so far, like all the great properties of Nash Equilibria. That is like, it has nice properties if we play like player we have never seen. We have algorithms that are like fast, easy to implement, and guaranteed to converge to Nash Equilibria. Everything breaks in multiplier. So I'm not too happy about doing multiplayer.
I have one question here. How many games did you have to play in order to reach the results?
So you mean the results, like after we got the DeepStack ready, how many hands we had to play versus humans? Or how many games for DeepStack were necessary for it to train?
Yeah, the second one.
Okay. So the way DeepStack was trained was a bit ugly. We would like it to play just from pure self-play, but we didn't really have time to do it. So imagine a stupid way to train AlphaGo neural network. You wouldn't do a self-play. We would just sample randomly a lot of Go boards. We would solve these Go boards, and that would create you like your supervised training data set, like a lot of this was my sample Go board, and this is the value of the situation. You would sample a lot of these and train neural networks on. This was unfortunately roughly how we decided to do it, because we didn't have that much of a time, and we needed like tens of millions of these situations.
Thanks.
Hi, thanks for the lecture. I have a short comment and a question.
Sure.
So the short comment is when you mentioned the chess opening, so there's this new AlphaZero program, which is like AlphaGo Zero improved even more, so you can play chess and Go and Shogi, and it discovered the chess openings by self-play. So that's kind of interesting and answer your question.
That's cool.
So my question is about the deep counterfactual value networks. I'm still a bit confused. Are they used in the playing, or only in solving?
Okay, so it's during the gameplay. Okay, so maybe this picture is the best one, even though it's not great. So the local reasoning procedure, it just rolls like a look-ahead tree forward, few steps, so it can start like a poker game tree for a few steps ahead. Then it cuts it in here, and is going to call the neural network. And when is it going to call it? That's a good question. So as it reasons, it needs to run this regret minimization procedure, the regret matching thing. So we typically need about 1,000 of these iterative process, and every single regret minimization process in a tree corresponds to a full traversal of this look-ahead tree, computing the regret matching formula, and once you are at the very end of the tree, passing the values to the neural network and getting the values back. So you will call every single neural network, you will call a neural network for every leaf situation in the look-ahead tree 1,000 times if you use 1,000 iterations of the CFR algorithm, and that you will average the strategies, because as we have seen, we need to average the strategies to get to Nash Equilibria, and then you will sample an action in here based on the average strategy, and you will do the same thing again.
Okay, I was just wondering, because when you play, you don't know the opponent's range, but for the network, you need it. So is it because you just sample some range of the opponent?
You start the procedure in here. There's no opponent range. There's just agent's range and opponent's counterfactual values. So you don't have to know opponent's range at all. The opponent's range is just a byproduct of the regret matching procedure in here. It's just a byproduct, but it doesn't doesn't correspond to the real range the opponent is holding.
So it's just some estimate, the opponent's range from the
In a sense, yeah, but it doesn't have to be like precise at all. Like it doesn't have to correspond at all.
Okay.
Technical question: do you consider even different ratio of players' budget to the big blinds?
I see. No, that's a great question. Like, I removed the slides because I thought it's too poker specific. But yes, so the great thing about this technique is the abstraction-based procedures had to pre-compute it for some particular game tree. So the one game tree would correspond to different like pot stack size ratio. But since we do local search, we just fire up the computation from any situation. So we don't really care what the situation is and what are like the starting blinds, what's the pot ratio. Like, it's just an input for the local search procedure that's done online. So whatever that is, we just solve for that particular situation. We don't have to know that in advance. So maybe a bit different answer, this can only play cash games.
Okay. Some more questions? Okay. So the DeepStack solved the just heads up no limit poker. Are you able now to solve also multi people tables?
So I've said like multiplayer poker is mess. Like it's mess on paper. Like maybe because it's mess on paper, humans also just play it very poorly. So maybe like something that's not so great will just beat them anyway. But like just taking DeepStack and putting it into multiplayer settings, all the theory breaks. So I don't know.
So I just see the analogy between the deep control factor of value networks and the value networks in AlphaGo. So I'm just wondering, did you also think about like analogy of a policy network for imperfect information games? Is there some
A what?
Policy network, a neural network that chooses the moves for the not just cut the like the depth, but also the breadth, the tree.
So yeah, I don't know how to answer. Like for us, we just like, to be honest, we didn't really do like proper deep learning like engineering / alchemy. We just like edit some layers and see what it does, because the deep learning piece is not the most important thing of the algorithm. It's like how we do the local search, and like the evaluation function can be anything. We just use like 7 layers rules because we didn't have time. So, but if the question is like, can you do better with the evaluation function? Absolutely. Like this is like very poor baseline architecture of the network.
Okay, thanks.
I have one more question. There are a lot of servers where you can play poker. Was there any reaction from their side, whether they were interested on, like, your opinion how people could, use your approach to earn some money on the servers?
Okay, so from the poker sites themselves, like Michael Bowling, he's the professor leading the research, and so he got an invitation from like poker stars in UK to like talk about what all that means for poker, and not surprisingly, like every single month I got like emails from like China, Russia, to like guys clearly implementing DeepStack and asking like some technical questions.
Okay, I see. Okay, some more questions? Okay.
Okay, thanks for the talk. Maybe just a theoretical question. Is there some guarantees of convergence of this procedure you mentioned?
Yes. So there's a guarantee on the speed of convergence of the regret matching. Okay, and one way to think of it is every single time you don't do like a precise regret matching. Like every single time you use value function to give you use the neural net to give you close enough values. So we have a bound that combines these, that says like if the neural network is like dead off from the correct value, and we run like long enough to get a guarantee of regret matching to epsilon, we can combine these to get like a guarantee of how close do we get. But it's of course it's bounded by how precise the network is.
But it's uniform on the number of steps. It's uniform on n.
On
the number of. Because you are calculating the value functions on the game where the state is the priors.
Okay. Oh, you mean of the number of like resolving steps? Like yeah. I see. No. Okay. It grows.
Okay. Yeah. Thanks.
Okay, one last question. Is there any? Okay. If not, thank you once again.